When calculating volume over circular or curved regions, standard Cartesian coordinates often lead to complex square roots and difficult limits. Today, we will learn how to simplify these problems by converting our double integrals into the polar coordinate system. Circular boundaries are naturally described by radius and angle rather than horizontal and vertical distances. By switching to polar coordinates, we can transform complicated boundaries into simple constant integration limits, making the calculus significantly more manageable. To convert, we use trigonometric relationships. The horizontal distance x becomes a times the cosine of theta, and the vertical distance y becomes a times the sine of theta. These substitutions allow us to redefine our function in terms of radius and angle. Crucially, the area element dA is not just drd. Because the wedge widens as it moves further from the origin, we must include an extra factor of r. Always remember that dA in polar coordinates is equal to r times drd. Putting it all together, the double integral of a function f, x, y, becomes the integral of f evaluated at r cosine theta and r sine theta, multiplied by the essential factor r. This formula is the foundation for all polar conversions. The limits of integration are defined by the region's geometry. Theta represents the angular sweep of the region, while r represents the distance from the origin. For a full circle, theta ranges from 0 to 2 pi. A helpful shortcut is the Pythagorean identity. Whenever you see x squared plus y squared in your integrand or boundary equations, you can immediately replace it with r squared to simplify your expression before you even begin integrating. Let's work through an example. Suppose we want to integrate over a semicircle with a radius of 2, located in the upper half plane. We need to determine the bounds for r and theta to set up our integral. If our function was x squared plus y squared, our integral becomes r squared times the area element r dr d theta. This simplifies to r cubed dr d theta. Notice how much cleaner this looks compared to using square root boundaries in Cartesian form. We evaluate the inner integral with respect to r first. The antiderivative of r cubed is r to the fourth divided by 4. Evaluating from 0 to 2 gives us 16 over 4, which simplifies to a constant value of 4. Finally, we integrate the result with respect to theta. The integral of from 0 to pi is simply 4 theta evaluated at the limits, resulting in a final answer of 4 pi. The polar conversion turned a difficult problem into basic power rule calculus. For an annulus, or ring shape, between radius 1 to find the area of this ring and 3, we integrate the function 1. Limits simply change to 1 and 3. Remember to still include the factor r from the area element. The setup is the integral from 0 to 2 pi and 1 to 3 of r dr d theta. Since it is a full ring, theta spans the full range from 0 to 2 pi. The inner integral gives us r squared over 2. Evaluating from 1 to 3 gives 4. Integrating for over the full rotation of 2 pi results in 8 pi. This matches the geometric formula for the area of a ring. To succeed with polar double integrals, always remember the extra r in your area element, use the trig identities to transform your function, and carefully sketch the region to find your angular and radial boundaries. Since it is the first quadrant, theta goes from 0 to pi over 2. The radius goes from the origin to 5. Conversion to polar coordinates is a powerful tool for simplifying problems with circular symmetry. If you got this, you are ready to tackle polar integration. Practice identifying these regions to make your multivariable calculus journey much smoother. This lesson was generated by Vision Solve AI.